In the last video, we gave a mathematical definition of how to represent or how to compute the hypothesis used by a neural network. In this video, I'd like to show you how to actually carry out that computation efficiently, and that is show you a vectorized implementation. And second, and more importantly, I want to start giving you intuition about why these neural network representations might be a good idea and how they can help us to learn complex nonlinear hypotheses. Consider this neural network. Previously, we said that the sequence of steps we need in order to compute the output of a hypothesis is these equations given on the left, where we compute the activation values of the 3 hidden units, and then we use those to compute the final output of our hypothesis, h of x. Now, I'm going to define a few extra terms. So this term that I'm underlining here, I'm going to define that to be z superscript 2 subscript 1, so that we have that a21, which is this term, is equal to g of z21. And by the way, these superscript 2, what that means is that the z2 and this a2 as well, the superscript 2 in parentheses means that these are values associated with layer 2, that is with the hidden layer in the neural network. Now, this term here, I'm going to similarly define as z22, and finally this last term here that I'm underlining, let me define that as z23, so that similarly we have a23 equals g of z23. So these z values are just a linear combination, a weighted linear combination of the input values x0, x1, x2, x3 that go into a particular neuron. Now, if you look at this block of numbers, you may notice that that block of numbers corresponds suspiciously similar to the matrix vector operation, matrix vector multiplication of x1 times the vector x. Using this observation, we're going to be able to vectorize this computation of the neural network. Concretely, let's define the feature vector x as usual to be the vector of x0, x1, x2, x3, where x0 as usual is always equal to 1. And let's define z2 to be the vector of these z values of z21, z22, z23. Notice that there z2, this is a 3-dimensional vector. We can now vectorize the computation of a21, a22, a23 as follows. We can just write this in 2 steps. We can compute z2 as theta1 times x, and that would give us this vector z2. And then a2 is g of z2. And just to be clear, z2 here, this is a 3-dimensional vector, and a2 is also a 3-dimensional vector, and thus this activation g, this applies the sigmoid function element-wise to each of z2's elements. And by the way, to make our notation a little more consistent with what we'll do later, in this input layer we have the inputs x, but we can also think of this as the activations of the first layer. So if I define a1 to be equal to x, so the a1 is a vector, I can now take this x here and replace this with z2 equals theta1 times a1, just by defining a1 to be activations in my input layer. Now, with what I've written so far, I've now gotten myself the values for a1, a2, a3, and really I should put the superscripts there as well. But I need one more value, which is I also want this a0 to, and that corresponds to a bias unit in the hidden layer that goes to the output layer. Of course, there was a bias unit here too that I just didn't draw on earlier. But to take care of this extra bias unit, what we're going to do is add an extra a0 superscript 2 that's equal to 1. And after taking this step, we now have that a2 is going to be a 4-dimensional feature vector because we just added this extra, a0, which is equal to 1, corresponding to the bias unit in the hidden layer. And finally, to compute the actual value output of our hypothesis, we then simply need to compute z3. So z3 is equal to this term here that I'm just underlining. This inner term here is z3, and z3 is theta2 times a2, And finally, my hypothesis outputs h of x, which is A3. That's the activation of my one and only unit in the output layer. So that's just real number. You can write it as A3 or as A31. And that's G of Z3. This process of computing h of x is also called forward propagation, and it's called that because we start off with the activations of the input units, and then we sort of forward propagate that to the hidden layer and compute the activations of the hidden layer, and then we sort of forward propagate that and compute the activations of the output layer. But this process of computing the activations from the input, then the hidden, then the output layer, that's also called forward propagation. And what we just did was we worked out a vectorized implementation of this procedure. So if you implement it using these equations that we have on the right, this will give you an efficient way, a relatively efficient way of computing h of x. This forward propagation view also helps us to understand what neural networks might be doing and why they might help us to learn interesting nonlinear hypotheses. Consider the following neural network, and let's say I cover up the left part of this picture for now. If you look at what's left in this picture, this looks a lot like logistic regression, where what we're doing is we're using that node, that's just a logistic regression unit, and we're using that to make a prediction h of x. And concretely, what the hypothesis is outputting is h of x is going to be equal to g, which is my sigmoid activation function, times theta 0 times a0, which is equal to 1, plus theta 1 plus theta 2 times a2 plus theta 3 times a3, where the values a1, a2, a3 are those given by these three hidden units. Now, to be actually consistent with our earlier notation, I actually would need to fill in these superscript 2's here. I guess need to fill in these superscript 2's everywhere. And I also have these indices 1 there because I have only one output unit. But if you focus on the blue parts of the notation, this is, this looks awfully like the standard logistic regression model, except that I now have a capital theta instead of lowercase theta. But and what this is doing is just logistic regression, but where the features fed into logistic regression are these values computed by the hidden layer. Just to say that again, what this neural network is doing is just like logistic regression, except that rather than using the original features x1, x2, x3, is using these new features a1, a2, a3. Again, could put the superscripts there to be consistent with the notation. And the cool thing about this is that the features a1, a2, a3, they themselves are learned as functions of the input. Concretely, the function mapping from layer 1 to layer 2, that is determined by some other set of parameters, theta 1. So it's as if the neural network, instead of being constrained to feed the features x1, x2, x3 to logistic regression, it gets to learn its own features, a1, a2, a3, to feed into logistic regression. And as you can imagine, depending on what parameters it chooses for theta 1, you can learn some pretty interesting and complex features, and therefore you can end up with a better hypothesis than if you were constrained to use the raw features x1, x2, x3, or if you were constrained to, say, choose the polynomial terms, x1, x2, x2, x3, and so on. But instead, this algorithm has the flexibility to try to learn whatever features it wants using these a1, a2, a3 in order to feed into this loss unit that's essentially a logistic regression unit. I realize this example is described at a somewhat high level, and so I'm not sure if this intuition of the neural network having more complex features will quite make sense yet. But if it doesn't yet, in the next 2 videos, I'm going to go through a specific example of how a neural network can use its hidden layer to compute more complex features to feed into its final output layer, and how that can learn more complex hypotheses. So in case what I'm saying here doesn't quite make sense, stick with me for the next 2 videos, and hopefully after working through those examples, this explanation will make a little bit more sense. But just to point out, you can have neural networks with other types of diagrams as well. And the way that neural networks are connected That's called the architecture. So the term architecture refers to how the different neurons are connected to each other. This is an example of a different neural network architecture. And once again, you may be able to get this intuition of how the second layer, here we have 3 hidden units that are computing some complex function maybe of the input layer. And then the third layer can take the second layer's features and compute even more complex features in layer 3, so that by the time you get to the output layer, layer 4, you can have even more complex features of what you were able to compute in layer 3, and so get very interesting nonlinear hypotheses. By the way, in a network like this, layer 1, this is called an input layer, layer 4 is still our output layer, and this network has 2 hidden layers. So anything that's not a input layer or an output layer is called a hidden layer. So hopefully from this video you've gotten a sense of how the feed-forward propagation step in a neural network works, where you start from the activations of the input layer and forward propagate that to the first hidden layer, then the second hidden layer, and then finally the output layer. And you also saw how we can vectorize that computation. In the next, I realized that some of the intuitions in this video of how other certain layers are computing complex features of the early layers, I realized some of that intuition may be still slightly abstract and kind of at a high level. And so what I'd like to do in the next 2 videos is work through a detailed example of how a neural network can be used to compute nonlinear functions of the input, and hopefully that will give you a good sense of the sorts of complex nonlinear hypotheses we can get out of neural networks.